I just felt like the computer hang, but let me also maybe connect from my tab. Then let's see. Okay. So so I guess what I'm going to do first is a quick review of like maximum likelihood and map that we ended last time. So we went for this example, but I didn't show you like the slides because I tried to ask you as questions. But let me just repeat this example again to kind of like we kind of have a quick review like what we have discussed. So we are basically we have three different cons here as we let me use a different color here. And you can consider like, as I mentioned last time, like we can start with like a bag, like somehow, and have three different cons here, C1, C2, C3. And I have different numbers of this type of cons. Like I may have like more C1 or like more C2 and so forth. And like C2 is unbiased, like the probability getting a head is the same as getting a tail, but like con 1 and con 3 are biased. So like I have like for con 1, it's more likely to get a tail than getting a head. So the problem we have is like, let's say we kind of like draw a con from this bag, and then we're going to like flip it a couple of times, and then we try to estimate. Okay, actually, there's two questions here. One is I try to which con we pick or we draw. The second question is like, if I flow this con again, like what will be the outcome? What will be the probability of head? Let's say, like what will be the probability of head? What is the probability of head if I fold the con again? Okay, I toss the con again. So we use this example to illustrate the difference of like maximum likelihood, basically ML, maximum likelihood method, map, maximum a posterior probability, and also like Bayesian. And by the way, like if we just ask the first question, you won't see the difference of like map and Bayesian. But if we try to answer the second question, you will see like there's a difference between MAP and Bayesian. But first, like for difference between ML and map, let's focus on the first problem. Will be simply like whether you apply it prior. So if I'm using ML, basically I will assume that like I have no prior knowledge of like which con I'm going to, I mean, which con is more likely to, which con is more likely to be that we get. So then in that case, we'll just assume that like it's uniformly likely to get like C1, C2, and C3, and all the probability will be just 1/3. Um, and uh, and in that case, for example, like if I have a hat, if I get a hat here, so then the maximum likelihood will be simply saying that like uh, the probability that to have a con one given a hat, because I am getting a hat really, right? Would be just simply 0.1 here. Um, Actually, it won't be because I need to normalize that. But let me just show this one here. So the probability of getting C1 will be simply trying to apply base rule here. So I will have like, okay, let's do base rule here. It is just like P C1H over PH, right? And then like I use base rule again, and then like C1H can be decomposed into PH given C1 and PC1 and PH here, right? So if I ask the question, like, okay, if I got a hat now, so what's the probability to get C1? Would be simply this one, right? And this one is looks know that like this is given by the problem, right? I know that if I have con one, then the probability of getting a hat is like basically like 0.1 here. This is I know that, and pH I can estimate that because I can estimate like this. So pH will be just equal to now again like this is a a review of like last time review is like we can do marginalization, right? This pH can be equal to like sum over pH let me just write these three terms here instead. That would be like pH C1 plus pH C2 plus pH C3, right? All we did here is just doing marginalization. And then we do base rule again. Each of these terms will become pH CI times PCI, right? So then of course, I know this. For example, like pH given C1 is 8.1 here. And this PC1 here, if we assume we are doing maximum likelihood, we don't know like which coin is more likely, then all of them will be 1/3. So you see that this is 1/3 here, 1/3 here, 1/3 here. And then doing that, like just do the computation, we will have something like this, right? So getting a hat, then the probability to get C1, C2 will be like this, getting C3 will be like this. Of course, we know that the con is more C3 is most biased to hat. So therefore, if we get a hat, intuitively we know that like it's more likely to get C1, C3. But here, like using base rule, we can get precisely what's the probability there is like 0.6, right? Now the difference here, okay, what we just did is maximum likelihood, right? The only difference here for MAP will be simply like here we'll assume that like we know the prior. So for example, like we know that okay, in the back here, maybe there's 100 cons there, and I have like 5 cons C1 and like maybe I don't see what's the number here. Let's see. Yeah, maybe like I will have like 100 cons there, and then maybe like 5 of them are C1. I have 5 of them of C1, and 25 of them is C2, and 70 of them is C3. Then I know the pi probability that like C3 will be highest, right? I basically will get I have like 0.7 probability that to get a con C3 from this back here. Now I can repeat this experiment, right? For example, like for getting a hat, what will be the probability? Will be simply the same equation, right? In this case, I will, I'm not writing the equation here. So let's see if I doesn't have that, but it'll be simply like PHC1 over the summation PHCI PCI, right? You just put the alpha here, but the alpha is essentially this normalization factor here. And PHC1 and so on, we know that. Like for example, PH given C1 is 0.1, right? And PC1 in this case is just like 0.05, and PC2 is like PC2 is like 0.25, PC3 is 0.7. Now again, I plug in all the numbers, then we can get like PC1 given H is equal to like 0.006, and like PC3 given H is like 0.8. Now this is like significantly higher because of course it's more likely to we have a higher prior for C3, right? There are more C3 cons in the back compared with like the C1 cons and C2 cons. Now, we can repeat that like when we have not just for tossing this con once, but maybe we toss the con twice. Maybe first time we got a head and second time it's got a tail. then we can repeat the whole thing, right? And the only thing is like now if I try to compute this, for example, like let's instead of write the alpha, let's do the summation again here as P4, sum over I like this, right? You see like, the only difference is that like I have something these two events tossing the first coin, not tossing the first coin. First time I toss the coin first time, I'm tossing the coin second time. They're conditionally independent, different which coins you're tossing, right? It kind of like obvious. So therefore, I can split this into like PH given C1, PT given C1, something like that. So then again, I know each of this term here, right? So then I know, for example, like this is 0.1 here. So P tail given C1 is 0.9 here. And then I can substitute everything and I will get the numbers here. I believe it's something like that, right? So something like this. Now again, I mentioned like we have two questions in mind, right? The first question is like which coin we actually draw we from that bag, drew from that bag. And the second question is like, um, if I toss that coin again, what will be the probability of getting ahead? So this comes the difference between like map and I mean the second question is like differentiate map and Bayesian influence. So for the first question, basically, if you ask Bayesian, it's still like trying to what will be the probability getting the coin is the same answer because what Bayesian did is simply trying to compute this value essentially. So if I want to say like what's the probability of getting a coin that coin is comfy given the observations, using Bayesian will be simply doing exactly the same thing. I'm trying to compute what's the probability of getting my desired outcome given the observation. So there will be no difference between Bayesian and map. But if I ask the third question now, if I sorry not the second question now, what if I toss this coin again? What will be the probability of getting ahead? Then for map or maximum likelihood, what it does is like simply trying to estimate which will be the most likely coin, and then assume that like, okay, that will be the coin that we have picked. And so therefore, like in this case, if I got a head and a tail in the first and second toss, then I will just believe that like if I am map or like maximum or actually if I am in this case it's a map estimator, then I would just assume that like because like 0.485 is the largest probability right amongst these other two here. So what map estimator does is like I would believe that like okay the coin is actually safely. So since the coin is safely, now if I ask like what's the probability of getting ahead next time, will be simply okay. I guess I probably should pause. I have kind of like talking non-stop like for 15 minutes. So so for map, okay, this situation here, I guess okay, for have a question here for map. I basically repeating a bit last time, but just make sure that you guys are following. For map, what is the probability of getting ahead? Maybe I should say estimate the probability. Estimate of getting ahead for the next toss. . 。 。 。 。 。 。 。 。 . 。 。 . 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 。 。 . 。 。 。 。 。 。 。
。 . 。 。 . 。 。
。 . 。 . 。 . 。 . So given the number showing in this line, on this line here, so basically you see like I have the setup is like I have the prior is C1, probability of C1 is like 0.05, probability of C2 is 0.25, but C3 is 0.7, and then like and also like for the first column, like probability of hat is like 0.1, for C2 probability of hat is 0.5, and for C3, for C3 the probability of hat is 0.9. And this is even computed for you here, right? C1 HT and like that. Like so now if I first toss, I got hat. This is the first one, right? I got a hat. Second time I toss the coin, I got a tail. Now I try to estimate what will be the probability of getting a hat for the third toss, let's say. So if I'm using like map here, so what will be the probability, estimate the probability of getting a hat for the next toss? Yes, yes, yes. Yes. Yeah, I just want to make sure you are following. You guys are following. Yes. So um now this is for map. Now for Bayesian, like the difference is like you see like map is like doing something like indirect. We first like compute kind of estimate what will be the probability of that coin, and then we compute the estimated probability. Now for map, sorry, for Bayesian, what we simply to do is like asking the kind of like answer this question like directly. So I have the probability of, so the observation is like getting a head and then a tail, right? Now the first, maybe I use a notation, something like that, head, or maybe it's okay, this is understood, like first head, second tail. Now asking what will be the probability that the first toss will be just a head, maybe I say the outcome 3 will be a head, doing something like that. So this will be the Bayesian approach of answering this question. So it's something like the most lateral actually, and but at the same time, like it may not be the easiest to compute. But in this case, it's not actually difficult. Um, so if I'm trying to find what's the probability of head given head and tail, that would be simply equal to probability of, let me just shorthand this as h given ht, something like that. It's understood like what I mean. H here is like the third toss is like getting ahead. It would be something like the probability that like actually the coin is C1, and what's the probability of like C1 given HT here plus probability of head given is C2, probability C2 given HT plus probability of C hat given C3, probability C3 given head and tail. Now you see the difference here is like I'm again I'm kind of answering with this like PC3, C2, and C1 here, but I'm doing a weighted sum, right? So you see like if I am doing a map estimation earlier, I will simply, okay, I'm sorry, like actually what I mean is I want to underline different things here. For if I'm doing map, the answer simply is this guy, right? Basically, I will be like saying, okay, I think that it will be simply safety. So therefore, I would say like the answer will be pH given C3 here. But Bayesian is more reserved in the sense that I will simply do a weighted sum here, right? I mean, it's very natural, right? I weighted sum of like all the probability of hat for uh, different scenario, different cons to be chosen, and weighted by the actual probability of that con given the observation. And so this is Bayesian, this is actually Bayesian, and you can see, especially for this example, you can see like Bayesian is much more reasonable because like uh, if you think of like the estimate from map here, it's not very robust because if I change my prior a little bit, I may become to have like C2 is the largest, right? I mean, this probability may shoot up here, this may go down here, right? And in that case, my estimate will jump basically from 0.9 to 0.5. Kind of like it's kind of like not a continuous jump. You can have a slight change of your prior, then you have a sudden jump of your estimate. I would say that this apparently is not a robust estimate. On the other hand, if you are using Bayesian, you don't have this problem. Like if you change your prior a little bit, it will be a continuous change of your estimate. But of course, if you see here, like if you have many different kind of like cases you need to consider, for example, like many different cons existing here, then this sum can become long, right? So compare with like map here, this can be a higher capacity in general. So Bayesian in general is a usually higher capacity, but theoretically it's the right thing to do. So I guess this will just finish that. You see, like if I'm doing Bayesian here, I will be simply doing weighted sum. Actually, yeah, okay, it will be equal to 0.68 whatever. So I guess it's better that he also said put HT here, but he didn't. Yeah, but it's okay. Yeah. So I guess in summary, let me just give a slide to summary this couple methods here. So this is you can think of like lots of problems like have a very similar setup. So you can think of like first you have some observed variables, like you did some observation, you know what is going on like from that. I mean, can use this observation to estimate some parameters. And the parameters in that case would be like C here, like if you remember which cons we're picking is like C1, C2, and C3 here. And the observation here may be like head and tail, like first toss is head, second toss is tail, and so on. And then I want to estimate something. Actually, I guess I probably can skip the latent here. I want to estimate like something like X is like what I'm interested in. Now doing maximum likelihood will be like I first estimate, actually both maximum likelihood and map will be first based on your observation. I'm trying to estimate the best parameter, basically the parameter that is maximizing the either the likelihood or the maximum or the a posterior probability. So for the likelihood, by the way, like it's essentially like if you think of for the map case here, if I have a map, but if I have a uniform prior, by the way, like if I'm doing map, what is this? This one is P theta given O is basically P theta O. I use base rule here, P theta O over P O, right? And my O here, like know that like I'm trying to just find the best parameter, right? Theta. So I'm maximizing over theta. So therefore, this is actually something like a constant, right? With respect to theta. So I can ignore this. and P theta O is equal to P O given theta, and then P theta. So if I'm doing a map, it's actually, I write like P theta given O is also the same as I trying to maximize PO given theta and P theta. And if I assume like this is like uniform, then like this would be like just a constant, right? This would be gone. So then like map will be like exactly the same as maximum likelihood here. And by the way, I think I may have mentioned that, but maybe not emphasizing that this is like called a likelihood function. Sometimes, oftentimes, like there's a given some parameter, that latent parameter, and or hidden parameters, and what's the probability of the observation. This is usually known as the likelihood. So again, like for maximum likelihood and map, here I will first estimate this parameter theta here based on trying to maximize either the likelihood or the posterior probability given my observation O. After that, I'll simply say like my estimate for X will be just the or like the probability of X, or maybe yeah, this is I will try to say, okay, the estimate of X, but I can also estimate in the previous example, I'm trying to estimate this Px here, right? So my estimate of Px will be simply equal to the max, or actually it will be simply equal to Px given theta hat here, something like. Yeah, and of course, if you want to further say what is the most likely happen X, well then like, I can find the one that have the maximum Px given theta hat here. So, but if I want to do Bayesian, for example, if I try to estimate what's the probability of X here, we'll be simply trying to estimate P, or like if I try to estimate Px, given my observation here, we'll be simply trying to estimate Px given theta and P theta given O, sum over all theta, something like that. And with this, of course, I can compute an estimate of X. We'll be simply computing the mean. So this is my Px given O, right? So therefore, like the mean or the estimate for X or the Bayesian estimate for X will be simply the expectation of X with this conditional probability Px given O. So I think this is very important, even though like this is a actually once you know that it's very simple, but I want to make sure you get that the difference. Map maximum likelihood Bayesian estimate, and especially like there are people like always got confused with map and Bayesian, and if you think of the Bayesian is something very natural, it's like whenever you try to estimate some probability, but that's why we call it Bayesian, right? You're essentially just doing Bayes rule here with your observation, and but you are kind of like summing for all the cases here, or all the possible scenario here. In our previous example, will be like whether you are getting con 1 or con 2 or con 3 there. So okay, I guess let me use the tab to draw instead. Maybe easier. to make myself co-host. Okay, I would like to continue to use this example. I mean the example of cons with like um, kind of tossing it several times and also like trying to estimate what's the outcome like of the next toss and so on. Now you see like in our previous setup, like we have one back here, right? And then back I have like 3 different cons. Let's see. Not exactly, actually. You will get different estimate. That would be a trade-off. I would say like Bayesian is the best you can do. At least like theoretically speaking. But as you will see later on, like it's not always feasible to do Bayesian, and that's why like people will kind of like go back to use like some maximum likelihood approach and like map approach. Of course, if you know the prior, you should always use the prior. So it's either you are doing map or like Bayesian. But the difference is like you, for example, like if you are using map, you have like let's say here like we just have like 3 cons, or we have like can have 100 cons here. When you're using map, like you just find a peak, like which con is more likely. And of course, you can have something much more difficult, like complicated. Um, and then once you know which con is most likely, you just focus on that con for your estimation. And typically, that complexity is way lower than you doing full Bayesian. And because I doing full Bayesian, you need to keep track of all the probability, and then you need to do weighted sum for everything. But if whenever you can do Bayesian, Bayesian is the most correct solution, basically, you can say. Um, but there are limitations, as you will see later on. Like mostly it's like computation. Um, and so, for example, like here, we let's immediately make the problem a bit more realistic. Here, earlier we just assumed the bag have like 3 different cons, right? C1, C2, and C3. And one con have like probability of hat, like this is probability of hat here. One is like 0.1, this is 0.5, this is 0.9, let's say. Now, you come to think of that, like, how do we get this information that, like, okay, in the back there will be 3 different types of cons, and then like one have this probability of hat is like 0.1, the other is 0.9, and so on. This seems to be really a strong constraint on the setup way. So in general, it doesn't look like we have much information. Most likely in a real scenario is like we don't actually know like what kind of cons do we have, right? We will have like we have like all kind of cons here, and I don't know like what's the probability of, let's say, for a particular con, I don't know whether that con will have a probability of hat will be precisely 0.9 or like 0.1 or something like that. Then does it mean that like we don't want to apply prior? So for example, like um, if I don't know anything, or I shouldn't say anything, if I don't know precisely like which I have like three kinds of cons, and then like for example, this C3 have like probability of 0.9 to get ahead. But I may have like some information. Let's say I believe that like um, those cons are more likely to be unbiased than biased, for example, or like I believe that um, most cons I will only have uh, yeah, or like the other way one anyway. So in that case, I may not want to just apply no prior, or like just assuming that like I mean everything is uniform. Um, we may still want to apply something. So let's look at like in this kind of scenario. Let's say again, I toss a first time is head. Let's say just look at like one scenario, like the first simplest case, I toss a coin, I got a head. Now again, I will have, I trying to estimate what's the probability of getting a legs head. Let's say given the coin is a head. Let's say now if I'm using Bayesian, as I mentioned, what I'm trying to do is something like I'm trying to say what is the probability of some coin. Let me define something first. Let me define Q as the probability true probability of the coin, true probability of the coin getting ahead, let's say. So now this is like the first toss I got ahead. I want to ask what's the probability getting ahead again in the second toss, right? So if I use base, what I'm going to do is I try to first estimate like what's the probability, what's that palm let me just write it, then maybe I say it. It's something like that, right? But actually, it's much more sense to do an integral here. So what I mean here is like, I would say, let's consider all cases here. Now, don't get like worried about the integral. You can just think of like, again, I'm doing weighted sum of like all this pH given Q, right? So I'm actually in this case, pH given Q is actually simply Q here. But okay, let's ignore that first. Wait a sec. My mouse is not working. My mouse is not working. Yes, actually, this is okay, but I'm thinking this may not be a very nice example here. Let's see, but I think I can still continue doing that. Yeah, okay, let me complete this since I already started that. So I have P, this is just equal to Q here, right? Q, and I integral this. I have this PQ given H here. And this PQ given H here, of course, I can kind of like, this is like the posterior probability, right? So I can use base rule again. I decompose this, maybe something like have a form P H given Q times PQ over PH, right? Something like that. And this, by the way, the PH here is like the observation here. This is not, this is just a kind of like a, what should I say? A constant because it's already happened. So it's the observation that you have H here. You may ignore that, like this is always happening when you have like PQ given H. You can always write this is proportional to this thing here, right? So your posterior is always like your maximum likelihood times your prior, right? So what I want to say here is actually when you, I have only one hat here, but I can have like more hats on tails. Maybe like let me give another example. Maybe yeah, I'm kind of like regretted like writing like this one here. So actually the thing like I only need to worry about is something like this. Like what's the PQ given like I have some observation here. Let's say earlier, like I have a hat here. I'm kind of only worrying about this. And this one is something like, okay, let me just make sure I don't confuse anyone. So this is saying like observation is hat, like given was the probability of Q here. And then like repeat again, like base rule, just want to H given Q times PQ over PO equal to H here. So here earlier I said like this is not important because this is already happened, right? This is already observed. I can ignore that for practical purpose. Or like later on, we can, yeah, let's ignore that. So now for this one here, like I have the prior, like previously I have the prior, and I have the likelihood function here. And the likelihood function in this case is simply if I have Q here, PH is okay, O equal to H is simply is equal to Q, right? Simply equal to Q, there's nothing. Now if I have, let's say, give another example here. I have PQ observation, like I not just make one toss here. Let's say I toss like many times, and let's say I have I toss like 10 times, and maybe I have like 5 head first, and then 5 tails afterward. So this is my observation. Then this will be kind of like, let me just write proportional, or maybe okay. Let me don't write proportional. Let me write equal anyway. P, I have like 5 head here, 5 head, and then 5 tail. Give Q here, and then PQ, and then over this P, 5 head and 5 tail anyway. Now, okay, just a quick question here. What's this value here? We call that like Q is the probability of the coin getting a head. Yes, given how is that related to Q? Let's say your observation, let's say like actually getting a head is Q, and you also have like 5 head and 5 tail. Was this given Q here? Yeah, actually I should that's sorry for like I I shouldn't here like need to expand this like this probably I confused confuses you. So let's just focus on this. So why we want this anyway? Even if we use a map estimation, let's say we consider map here, like as we discussed earlier, map. If we do a map, let's say like I have some oscillation like 5 head and 5 tail here, right? Then the question is like, okay, I want to maximize up max this Q here. My estimate Q here would be simply this way. And then would be equal to this thing here is equal to P hat tail given Q PQ over this thing, sorry, hat. And as I said, like this denominator is not important because it's independent of Q here, right? So I can pull it out or I can simply ignore that. That's why, like I said, like earlier, this one you typically we don't need to worry about that. And for this map estimation, right, it would be just equal to trying to maximize this. It'd be equal to again, it's like just the maximum likelihood value multiplied by the prior. Now my question is like, what's this maximum likelihood here? Question here. Just like for the notation we use here, like Q is a true probability. So of course this will be related to Q, right? My this answer should be like something like something a function of Q. It should be some function of Q, but what's that function? How is that related to Q? Say I have like this is 5 head and 5 tail, right? So let's say if I just have one head, uh, let's say if I just have one head, and the question is like, if let's say for this one, I guess like this one probably will resolve some confusion here. Q here is like the true probability of getting a head, right? Let's say it's the value is Q, and like given Q here, PH here will be simply equal to Q, right? Because like this is like the definition, right? So it's saying that Q is actually the probability of getting a head. Now I ask you like what's the probability of getting a head is just Q, right? Here, right? Now if I have like PH tail, let's say head and tail, like I have two tosses here, one getting a head, one getting a tail, then this will be like just Q 1 minus Q, right? So now back to this one. So what will be the probability of getting 5 head and 5 tails? Yes. So in general, like let's say if I have let's say X head and then Y tails, so I will have Q to the X and then 1 minus Q to the Y, something like that, right? Okay, this is the maximum likelihood function. if I want to do Bayesian or map estimation, I need to include the prior, right? Multiply by PQ here. Now the issues now is coming. So there's a decision choice here. So what should we pick for PQ here? So this is like something arbitrary, right? Uh, as long as this is some kind of function, you can think of like this. If like this should be like some kind of function here, let's say FQ here, that can be parameterized by something, like maybe some parameters here. So I can tune this prior as long as this function is flexible enough. Then that is kind of cool, right? For example, like I may have like some kind of function here able to characterize that like I will have like more head than tail. Like let's say I can have like this is like this PQ here. Maybe I can have a function like this, saying that like this is a probability of Q. I have like more cases that um I will have head than a tail. Like in this case, like right, this is Q here. Okay, come to think of that, like I always find this pretty kind of like I should say like kind of drive my brain a little bit crazy because I um oops, but careful. I mean, be careful that like we are talking about like probability of probability, a distribution of probability here, right? Q itself is a probability. Now we are talking about like how Q is distributed. So we are doing a kind of like second level of probability basically. Like we have one level probability, then let's talk about probability of that probability. So for example, like yeah, yeah, exactly. So here in this case, for example, this will be okay. Maybe just want to make sure that like you guys are following me. For example, like for these two distribution here, so which one is more likely to have got a head? Like this is A and B. So which situation is more likely to get a head? Yes, uh, because I for this one we have more Q. Q is like more likely to be higher, right? So we have like P clear, the larger Q, and this one like Q more Qs to be smaller, right? So therefore, like A is more likely to be had, like the case A is more likely to be had. So now back to this one here. So we have like lots of choices here. So of like how do we define this pi probability function or like distribution? Uh, but it seems to make sense that one very reasonable choice is that like how about we try to like define this PQ here have the same form as this maximum likelihood. Then when we multiply these two together, then we'll have something is much more manageable, right? So therefore, like it looks like a good candidate for this PQ function, or like you can think of like this function can be parameterized by some parameter here, can be something like q to the n and 1 minus q to the m, something like that. And of course, like this in general is not a probability distribution, right? Because for this to be a probability distribution, I need to make sure it's normalized. So this should be like equal to this. Okay, let me write like this. It's over q to the n, 1 minus q to the m, dq from 0 to 1. Note that q is a probability itself, right? So therefore, it can only lie between 0 and 1. So basically, I can define this pq to be this when q is like between 0 and 1, and 0, yeah, 0 and 1. Otherwise, it's equal to 0. So if I define something like that, like this thing, of course, like this is now a kind of like a function related to parameter m and n, right? N and m here. And if I multiply this likelihood function here with this pi here, I'll have some form like qx plus m, qx plus n, 1 minus qy plus m. So it's like I have the same form as before. It should be like easier to manipulate. And this is like something very common, uh, commonly used. And in general, when you have like this prior have the same form as the likelihood, and therefore like it's also the resulting a posteriori probability also have the same form as the maximum likelihood, then this prior is known as the conjugate prior. So you have a table. If you do a Google Wikipedia and you look for conjugate prior of like different distribution, it will tell you like what distribution, what's the conjugate prior distribution of like each of the random, different like random distribution. For example, like um, in this distribution we talk about for this tossing, um, this is really a binomial distribution, right? So it's something like if you do it like um, something like uh, counting win and success. I also like success and failure, like doing n trials, like how many times is success, how many times failure, and this gives you a binomial distribution. And the conjugate prior, this one, is actually the beta distribution. So, okay, I want to make sure you understand conjugate prior here. And also, like, I'll spend a little bit some time just go for like beta distribution is like, um, uh, if you play with like, I mean, like, this is like actually very common because like for this binomial or like binomial trial, this is a very common kind of experiment people will do. Right? Think of like contorsing or like any kind of event is binary. If you do it multiple times, you want to see like how much time you fail, how much time you success, and so on. And all those will be described by binomial distribution. And here I kind of like simplify a little bit for actually I kind of like I a sec. I kind of it's not I lie, but I think I kind of like I did not follow the convention here. Just make sure I didn't confuse you earlier. So for beta distribution, usually like they define with like a -1 here. So instead of n and m, they call it, let's say, a -1 and 1 minus q, b9 -1 here. So, but it's just like changing the parameter like from n and m to like have a -1 here. And the normalization factor, this guy, of course, will become like a -1 and b -1. And this factor, if you compute that, like is equal to something we call beta function, like BAB here. So this, therefore, like this is a beta distribution, beta Q parameterized by A and B is equal to something like that. Oh, reset. A minus 1, 1 minus Q, B minus 1, something like this. Now, I like to just do some manipulation of beta distribution. In particular, I like to mention like this nice thing about this normalization factor. I mean, this kind of trick because it can be used like beyond beta distribution. I guess therefore it's worth mentioning it here. So this BAB, of course, you can try to compute this integral, and I would simply skip that, like doing that. But if you try to compute the integral, you'll find that this is actually equal to some special function gamma A, gamma B over gamma A plus B here. And the gamma function, by the way, like is equal to, I guess, let's see if I can copy here. Probably I cannot. Okay, maybe I'll just rewrite on the next page here. So as I mentioned earlier, I have this beta function, beta QAB is QA minus 1 minus QB minus 1 over beta, should just BAB here. And this BAB is a gamma A, gamma B over gamma A plus B. And or like this is of course is actually just the normalization factor. Something like that, right? So if you go through the integral, you'll find this, and where the gamma function is equal to something like that. Oh, by the way, just a poll here, like a poll question. Like, so did you see this gamma function before in other courses, a special function? Encounter this gamma function before? So I'm not sure. Like, so okay, okay, don't worry about that. Basically, I would say like as an engineer, almost the only thing you should really remember and is really should know is like gamma function is very much related to it's an extension of the factorial. So actually in general, you have like gamma C is equal to C minus 1, gamma C minus 1, something like that. Of course, you can prove that. Like if this definition, you can prove that. Like it's just integration by part. And in general, like what you get will be something like if you have like integer, let's say gamma n here, n is an integer, it's just n minus 1 factorial. And this one is a very useful fact here, very useful, very convenient fact here. And it's almost like everything you need to know about gamma function. I never remember this definition. I can take it up in Wikipedia or something, but I will try to remember this because it's very convenient. So I will kind of like convince you why it's convenient. For example, like let's see, I'll just give an application for this one here. Let's say if I try to compute the expectation of a beta function. So if I have a distribution like this, given A and B, right? This is I have a distribution. Of course, this is a distribution of distribution. It's a distribution of probability from 0 to 1, right? So with different A and B, I can have like different shape like this, right? For example, this can be some A and B. I'll get this PQ is like this here. Now I can ask what's the mean of this PQ, of this Q, right? So this will be simply the expected value of Q. So expectation of Q, so for example, will be just equal to Q, this will be an integral, right? Q is continuous, so it's an integral beta Q A B, right? Something like that. And Q should be from 0 to 1, right? And I have QAB is equal to something like that. I can write down like Q A minus 1, 1 minus Q B minus 1. This BAB here, right? BAB. Or I can write it explicitly, maybe gamma A, gamma B, gamma A plus B here, dq. Now note that like I have q here, qa minus 1 here, so I will have like q to the power a, right? 1 minus q b minus 1, 0, 1. And I have gamma a, gamma b, gamma a plus b here, dq. Now note that like I have, what's this integral here? So all these are kind of like constant, I can pull it out of the integration, right? Out of the integral. And the remaining part here, oh, okay, maybe this is a question here. What is this, like in terms of beta? Beta what? Okay, let's look at this one first. Say 0, 1, q a minus 1, the original one, right? Q a minus 1, 1 minus q b minus 1, dq. So remember, like, okay, know that like this BAB, this one is a distribution, right? So what's this? Okay, let me erase this question. What's this? So this, what's this one? What's the integral here? Yeah, let me cancel this question for now. So what was this integral here? I told you that like this is a beta distribution of Q and A with parameter A and B. This is different from here. Note that like I'm doing something different. Like this, I didn't multiply by Q here. Here I didn't multiply by Q. I just I have no Q here. Earlier I have multiplied by Q, right? So therefore this is not the expectation of Q, but just this one was this one here. I'm simply integrating the distribution from 0 to 1. Yes. So now you see that this one equal to 1. What does that mean? That means that the integral 0 q a minus 1, 1 minus q b minus 1 dq is equal to just bab, right? Now I can, so now it become this one, I think is very simple question. Let's go back to this one. So the question is like the integral of this, I have a instead of a minus 1, what will be like this integral now? it will be B of this will be B again, right? But no, not the yes. This will be simply B A plus one B, right? No, I guess I can finish that. I will take a break. So this is B A plus one B. Actually, that's you just know that like I write the integral, but I'm not doing any of the integration. That's the beauty here. The only thing I remember is like the fact that like the beta, the b function here is actually just equal to this gamma function here, and then like the gamma function have this property that gamma c is equal to c minus one times gamma c minus one. Then the magic come, right? This one is equal to ba plus one b. So therefore, like this one was ba plus one b would be like gamma a plus one gamma b over gamma a plus 1 plus b. Now this is like divided by gamma a, gamma b, gamma a plus b. Now I can use this fact here. So gamma a plus 1 is equal to a times gamma a. So this will be just gamma b here. And then the denominator here would be like, oh, wait a second. Yeah, gamma a plus 1 plus b would be like a plus b times like gamma a plus b. Then I can, of course, I can rewrite this a plus b, gamma a plus b, gamma a, gamma b. Now I can cancel everything here. So then I will simply get a over a plus b. So it's very nice. We didn't actually do any integration here, but you see like just knowing this fact, I'm knowing that like BAB, I'm knowing that like because you normalize everything to 1 here, the scaling factor here must be just equal to the integral itself. So therefore, like you can, and actually, you may try to do this. Like, what's Q's the expectation of Q square? I don't know. Maybe I will leave it to you. Like, be a bit busy. This is a question for you guys. And then we will take a break. I'm sorry. Like, so I take a break. I mean, like, yeah, it's okay. Like, you can take a break and then come back to this question. But I will just leave this question here, and yeah, you can think about that during the break. Yeah. So okay, let's come back like 4:30 again. Yeah. Okay, let's continue. So hopefully you guys are back. Did you try to compute this? Like this expectation of Q square instead of expectation Q? So my expectation q square should be q square my beta function, so will be like q a minus 1, 1 minus q b minus 1 over b a b, something like that, right? dq from 0 to 1. And so it's more or less like the same as what we did earlier. So anyone able to complete that? So I can absorb this into this one here, right? So I have q, I have a plus 1 instead, 1 minus q, b minus 1, dq, 0, 1. I can write like 1 over bab here. So this one I can compute the, okay, in the same manner. What's this one here? Will be equal to ba plus 2 and b, right? So I have ba plus 2 b over bab here. And so what will be that? I guess maybe I will just stop here and then so let's continue. Like what will be that? Like, can anyone? Yeah, I guess maybe you guys are not back yet. I don't know. Okay, so it's able to find that also ba plus 2. So this, therefore, expectation q square is equal to b a plus 2b over b ab, right? So can you complete that? It should not be very difficult. So again, remember, like, no. Actually, the point is like you see the integral, but we don't want to play with the integral. Yeah. So here, just because we know that like q a minus 1, 1 minus q b minus 1, b a b here. I mean, this one is a beta distribution. Therefore, integrate this will get 1. So therefore, I know the integral here, the numerator is just equal to BAB here. So therefore, like, it's very easy for you to compute this and get like this should be just equal to BA plus 2, B over BAB, something like that. And remember that like BAB is the gamma function, like gamma A, gamma B over gamma A plus B. And you should know that like gamma A is equal to A minus 1 times gamma A minus 1. And just using that, you can compute this very easily. So what will be that? So see if you guys can complete this. Oh, I want you to simplify this further. Like as you can see, like this one is equal to this, right? As mentioned earlier, this q square multiplied into that are qa plus 1 minus qb minus 1, right? And this one is actually just equal to ba plus 2b. So therefore, like this one eventually be just equal to this one, right? Q. And then you can further simplify this with these things here. We know the b function is just like gamma a, gamma b. Yes. And then like gamma a, you can simplify very much, like into something like just something very simple, basically. Yeah, pretty simple, I would say. Yes. Yes. Remember this also, like the gamma function is like very much like a factorial function. It's actually an extension of factorial function. If gamma a is equal to a minus 1 times gamma a minus 1. Uh, Not quite right. Let's see. So uh, you have this one over this one. Uh, oh, okay. You haven't finished yet. Okay. So I have like BA plus 2B is like gamma A plus 1. Um, sorry, like gamma A plus 2, gamma B over gamma A plus B plus 2, or something like that. BA over B, oh, sorry, over BAB is like gamma A, gamma B, gamma plus B. Okay, okay. Maybe I'll wait for you a little bit. Now, this got cancelled. I remaining I only have this. How do I simplify that? I have gamma A. Okay, yeah. Yes, you have gamma A over A plus 2 over gamma A. You have like gamma A plus 2 over gamma A. And you have like gamma A plus, okay, gamma A plus B over gamma A plus B plus 2, right? Now, note that you have this. You can use this to simplify this much further, these two terms here. Mm, uh, I think we probably ran into some typo earlier. So gamma only have one argument. So here, like you may be talking about BAB and so on. I know that like BAB is like has two arguments is equal to gamma A, gamma B over gamma A plus B here. Oh. Okay. I don't want to confuse you, but gamma n in general is not in general. You know that like what I have here, know that when a is an integer, what do I have is like gamma a, or like let me write gamma n. Gamma n is equal to gamma yeah, let's see if I can help you like on this one. Gamma n is equal to n minus 1 times gamma n minus 2. Now gamma n minus 2 is equal to n minus 2, right? And gamma n minus 3. And this gamma n minus 3 is like gamma equal to n minus 3, gamma n minus 4, and so on and so forth. Eventually you got like gamma 0 if you have integer, and gamma 0 is basically equal to 1. So therefore, like gamma n, like, okay, hopefully I saw it making some confusion, but when n is integer, so therefore you get like gamma n is equal to n minus 1 factorial. But this is just simply coming from this equation here. And of course, you need to know gamma 0 is like, or gamma 1 is equal to, uh, gamma 1 is equal to 1, something like. So you have this here. Know that you can use this a couple times, right? I have this one here. I have like gamma a plus 2. I can write is equal to what? It's equal to a plus 1. Yes, you guys got it, right? So is equal to a plus 1, a gamma a, right? Yeah. So then you got something cancel. Then you will have, yes, that's pretty nice form. So um it's basically like there's no special function, no gamma anymore. It's just a couplet, a couplet division of like two like polynomials. And of course, I with that, if you know EQ square here, you can compute the you can now compute the variance of Q. Remember, variance is just equal to EQ square minus E q square, the mean square. So we showed that like in the first class or something like that, I forgot. And then like you know eq square just earlier, you know e square q. Then okay, I just skip that. This will be equal to a plus b square, a plus b plus 1. Oh, of course, you can find that in Wikipedia. So, but I mean, like when you're offline, knowing this is very convenient if you want to solve something very quick. Like, for example, maybe the airport, even at the airport, like you have like Wi-Fi, but maybe like you don't want to pay on when you're on the plane, and then starting working on that. Like this is very convenient. Like you can find the mean variance and so on like in a couple minutes yourself. And okay, let's now back to we talk about this beta. So let's just beta function here, or like the beta pair here. We mentioned this is like the conjugate pair of binomial distribution. So let's say this is a, let me just write the form again, something like that. 1 minus q, b minus 1. Let's be a b here. Now let's do some actual inference. Let's say I want to find the probability. Let's say okay. We let's say we have the pair is AB. Okay, let's say that. Like let's say I flip the coins n times, right? And I observe like x hats here. X hats here. Now, if I compute what's the probability of this observation, let's call this observation O here. The observation O here, and also given the prior, I use this prior, the beta prior here, right? So, and I want to find the probability, the distribution of this Q here was the distribution of the true con has probability, yeah, the true has probability of the con, given the observation and given the prior that is beta and AB. And we know that this is proportional to my prior probability, QAB here, right? And also like the observation given Q here, right? Okay, it's proportional to that. And I write proportional to that because you have like some scaling factor here, but these are not, this is maybe I even write K here, let's say. Is equal to K here, is some constant. And this constant, like constant with respect to Q. With respect to Q is a constant, okay? So let's see, like, let's try to simplify that. I have K beta distribution is like, okay, I have BAB here, and QA minus 1 minus QB minus 1 here. Well, okay, what is PO given Q here? This one is like, if my true probability is Q here, I toss the coin like n times, I got X hat, right? So that is like the binomial distribution. This is like basically Q to the X, right? 1 minus Q n minus X. Actually, I forgot the scaling, forgot the factor like earlier, but it doesn't really matter too much for our discussion. But it's okay. Like I earlier I said like 5 heads and then 5 tails, therefore my result is correct. But let's say if in general, let's say if I just toss the coin 9 times, I just say I got X hats here, then the probability of getting that will be this one, but I need to multiply something, right? Because I have like multiple scenarios. I can get X hats out of n tosses, right? For example, I have 10 tosses, say, or like maybe even just 5 toss, n equal to 5, and x equal to 2. I can have like head, head, tail, 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 or like head, tail, 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 head, and so on. Like each of these will have probability like q to x 1 minus q to n minus x. But the number of them will be what? Will be just NC2, right? Oh, sorry, like instead it's a 5C2 here, but in general here will be just NCX, right? So like n factorial x factorial n minus x factorial here. Or this is NCX here. But it's not very important because this part again, like constant, it's a constant here, right? With respect to q again, right? There's no q here, so therefore it's really constant. So what I get is like, okay, I can put all the constant together, say this is k1 or like another constant here, k1. Now I group this q and x to q and 1 minus q together. I have q a plus x minus 1 here, and 1 minus q m minus x plus b minus 1 here, right? And this is what? Basically, this is what? This is beta q of what? This is a question. Are you guys like following? So we start with like again like what we start with like we try to ask the question again. Like we have some observations. It's like we toss the coin n time, and then we got x has here, and we also have some pi information. We assume the pi we're using is a beta distribution with parameter a and b, and now we want to look at the posterior probability. The posterior probability given the observation and given the prior. And I went through several steps here. Eventually be equal to this, right? Now I have a quite simple question here. Is what what is what has I just written? Like I would say it's a beta distribution. This is a beta distribution because it's for a beta distribution, it simply have a form of like a beta distribution with a variable like q here will be just q to the power something, 1 minus q to the something, right? And with some scaling factor like BAB here. So this will be like some beta distribution as well, right? And what's the parameter here of this beta distribution? Yes. So this will be simply like a plus x and n plus b minus, or like, yeah, b plus n minus x, right? So you see like, okay, what's happening is like, if we start with like a beta prior with a and b, yes, beta pi with a and b, after the observation, they are observing like uh, n toss of x has here, I will have that parameter simply become like instead like my a new like my new a will be like a plus x, and then like b will be like b plus n minus x. Simply like I have like x hat x more hats, I will just add this x to A here, and I have n minus x so much more tails. I'll add that to B here. So that's it. Know that one thing here, I guess I didn't kind of like a little bit cheating here, but I was not wrong here, but I kind of like kind of jump through that quickly um, without explaining rigorously. So how can I do that? Like saying this is a beta distribution. Okay, here's a form like this, right? Yeah, definitely has a form like this. But I have a scaling factor like k here. How do I know this is a beta distribution instead of like some beta distribution multiplied by some constant here? Why not this beta q multiplied by some k2, let's say, where k2 is not equal to 1? I'm basically, I just like claim immediately saying that, okay, this is actually a beta distribution without any scaling factor here. It's just equal to beta q a plus x b plus m minus x, but not something like k2 times beta q a plus x b plus m minus x with k2 not equal to 1. So know that I can do that because this is really like, even though I have all this constant, if I look back my first original term here, this is really a distribution over Q, right? So therefore, it should normalize to 1. And if, let's say, if I equal to K2 something, I'm trying to kind of integrate it over kind of like the entire Q space, like from 0 to 1, I should get 1 here, right? And of course, I integrate like this thing here, or because or what I'm saying, like, if I integrate like this one here, like on both sides, if I integrate both sides, so on the left-hand side here, this should be equal to 1 because this is really a distribution of Q, right? It should integrate to 1. And the right-hand side, this will be equal to K2, right? So therefore, K2 is simply equal to 1. So therefore, this is really a beta distribution, but not a scale version of the beta distribution. Okay, uh, so much for that. So let's see. Let me erase part of this here. Now let's do a final question here. So this is on beta q. I have a plus x, b plus m minus x here. So if I need to estimate this, no, note that this is, I'm just saying this is a distribution, right? So how about if I want to get an estimate of q? Now I estimate q. I can do a couple of things, right? If let's say map, maybe Bayesian. So I won't say maximum likelihood because I already introduced this prior. Apparently, it won't be maximum likelihood. So if I try to estimate this Q now with either map or Bayesian, okay, maybe we can start with Bayesian. So if I want to estimate Q with Bayesian, I given that probability Q is equal to this. So what should be my estimate? So this may be a little bit required you to have pretty clear mind for this entire class, um, relatively. Um, so if I try to do a Bayesian estimate, what should it be? A Bayesian estimate is the weighted sum of my, for example, like if I want to estimate something, like this is a power distribution, like something. If I want to estimate like as a FQ, that is a function of Q here. Using Bayesian will be something like the expectation of FQ, or like something like is equal to FQ integral PQ given OAB, right? Now I'm not estimating some FQ. Actually, I'm simply estimating Q here. So therefore, like I'm actually my Q estimate is simply, maybe I write as Q hat here. Q estimate will be simply Q times PQOAB. I'm integrating the entire um like Q like from 0 to 1, and or simply the expectation, right? Expectation of Q here. And we know the expectation of Q here earlier, right? So what is that? So this is equal to um, A over A plus B, I believe. So therefore, like this is actually equal to, or like A tutor over A tutor A plus B tutor. So therefore, this is like A plus X, A plus B plus N, something like that. This will be my estimate of Q using Bayesian. So if you look at the number here, it's more or less like very natural, right? You can think of like uh, A and B. You can almost think of like A and B is some how much time you the experiment you did earlier, right? So something like A plus B is how much time you tossed the coin earlier, and then like out of that, like 8 times of that like are heads. Now you toss the coins like n more times, and then like you got X heads here. So now you estimate well what's the probability of head? Will be simply A plus X, that's total number of heads, over the total numbers of tosses here is A plus B plus N. Now this is the Bayesian estimate. So how about the map estimate here? For the map estimate, I okay, let me it's okay. How do I do map estimate? So for map estimate, I should find the Q hat will be the, so this is for map here. For the argument that maximize like PQ given OAB, right? So, or like this would be something like the R max of beta Q A plus X, B plus M minus X. So meaning that I need to find the mode of this distribution, beta distribution here. And you can do it yourself, like by just simply taking derivative, like for example, like you have this beta here, you take the derivative d beta dq here, then you will have like something a minus 1 q a minus 2 1 minus q blah 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 blah. I'm set it to 0, right? Then you will find the peak there, and I'll just leave it to you. Like the peak there or the mode will be something like a minus 1 over a plus b minus 2 if you have a beta distribution with parameter a and b. And so therefore, like for this one, actually I should leave the map estimate here, the Bayesian estimate here. The Bayesian estimate is like a plus x, a plus b plus n, something like that. So for the map estimate will be a plus x minus 1, a plus b plus n minus 2. Yeah, something like that. So this is the map estimate. Okay, let me give some numerical numbers and maybe so hopefully it's it's easier to follow, and I want to make sure that like uh, you guys are following. So let's say if I have A and B. By the way, actually I didn't um, let me rewrite this beta again. Like beta q a b have a form like q to the a minus 1, 1 minus q, b minus 1, right? Over a b here. So okay, this I will just really give a question and I let you to think about that. If I want to introduce a non-informative pair or uniform pair, non-informative pair, what should be A and B? So I'll give you a minute something like just look at this. Okay, to think about that. Like it shouldn't be too. It's not should not be too um, difficult. You just look at this. Like what will be the uniform pair? Actually, the non-informative pair. Non-informative meaning that like okay, I say it's uniform because like when this is a constant, right? If it's then remember this is pi. I'm going to multiply this to the maximum likelihood function to get a posterior probability, right? So if this one is a constant, that it means that it's just not there. So what A and B should be so that like beta will be non-informative. For example, if you don't know anything at all and you don't want to give any opinion, you still want to do something Bayesian, you still want to apply a beta here. So what should be your A and B? So that like it's like there's two parameters, A and B. You need to say both A and B. What will be A and what will be B? But your question is actually your answer is kind of right. At least one of you guys are right in the sense that you want to have beta is equal to 1. But what A and B should be like for beta to be 1? For your prior probability to be 1. Close. Yeah, close. Um, so look at this form here. Like if I want this to be constant, like in the sense like beta does not depend on Q, what should I set A and B? yeah, it's correct. I set b equal to 1, right? If I set b equal to 1, this will be gone, right? This is 1 minus q to the 0. This will be gone. So what should I set a? Yeah, yes, right. So then if I set both a and b equal to 1, so therefore, if for a non-informative pi, it would be simply beta q and then 1, 1, something like a and b and just 1. Okay, let's consider a non-informative pi here. And you just continue, just put in some numerical values for our discussion earlier. So now we have a equal to 1, b equal to 1. And remember that I have this a tilde, b tilde, the new one will be simply, simply, yeah, yes, that's, yeah. So simply x, if I toss the coin n times, I got x hat, so it will be a plus x. And then the parameter will be b. Okay, b plus n minus x, right? Okay, will be replaced by that as we discussed earlier. Now, okay, let's put in some numerical value for this, and then let's say I already decided my pi has to be 1 and 1 to be non-informative. Now let's say n is equal to 10. I toss it 10 times. I got x equal to 0. I got no hat at all. Now, so what will be my estimate of q? Okay, let's see. So with this first, what will be my distribution p q given my observation a b? From earlier will be simply equal to a beta distribution of q. Now a is equal to 1, b equal to 1, right? X is equal to 0. So I have a is still equal to 1 and b is equal to 11, I think, right? So it's 1 plus 10 here. Yeah. Now this is basically the distribution the posterior distribution I got. Now I can do map estimate and Bayesian estimate here. You might probably need to flip it back. Okay, I will ask you what was the map estimate. What's the map estimate first? The map estimate, what's the numerical value for probability? What's the map estimate of Q? What is Q hat? Like something to estimate of Q. So I guess an earlier slide will help you. So the map estimate should be something like this, right? You just simply should plug in the numbers here. So A equal to B equal to 1, N equal to 10, X equal to 0. I flip it, I toss it 10 times, and I got no hat at all. Now I estimate the probability of hat of that coin. Like something like, okay, now given the information here, what should my believe the coin, the probability of the hat of that coin using map estimation? Yes, yes, it's just 0. You substitute that. Now, how about Bayesian? Again, very simple actually. How about Bayesian? Yes, right. Um, and I want to give a remark on that. You see, like map estimate here is quite extreme. So you can think of maybe yeah, I toss it 10 times, you get no hat, then yeah, it's very much small chance like that probability of hat is anything. But I can set it not 10 here, maybe I set it 3 here. Still I will get 0 here, right? So it seems to be a pretty outrageous claim, like saying like you toss the coin like 3 times, and then you say, okay, there's no chance we'll get any hat anymore if you use a map estimation here. Because like, for example, I toss it 2 times here, I'll still get a 0 here, right? If I toss it 2 times, if I start with a non-informative pair like AB equal to 1 here, I toss it 2 times, and if I got no hats here, I would just say, okay, that's impossible to get a hat. That's my conclusion from map. Um, on the other hand, for Bayesian, like if I let's say if I 2 times, like if I change the setup is 2 times here, then I will get like the probability is like something like one fourth, I guess, something like one fourth. So it's this is small, but it's not extreme. Like so in machine learning, this is called like known as account regularization. This like Bayesian is automatically the outcome or the estimate from Bayesian is automatically regularized. Uh, because you think of like what Bayesian did, like deep down, like behind the black box, it's always doing some weighted sum. So it's like averaging like different scenarios. So therefore, like through the process, like they just average out those extreme cases. So therefore, like you will get results less extreme. So but on the other hand, for map, you can get you just look at the the most probable one, or like I shouldn't say that. This is like very so pick the one like with the highest probability and stick to that. And that one uh, mm, depends on cases. You may get a quite uh, extreme estimate. So that's a remark um, I want to put kind of like a take home message, something like. So, okay, let's see. Do I still have anything else I'd like to talk about for beta distribution? Maybe not. Let me see if I miss anything, something that I like to talk about. Uh, I guess I'll just quickly, I won't go detail, like, but just like briefly mention like Dirichlet distribution and multi-normal distribution. So I won't kind of like go deep detail like in anything like that. But just in case because they are also very popular, very useful. Um, you're likely to encounter Dirichlet distribution in the future. At least uh, I, I want you to get covered. I mean, um, and actually, it's not difficult. Like you can look at the notes and then like there's more detail like written down there. But I just want to like give you the high level concept here. So then like when it's needed, you can just go back. Like you and then take a look. Yeah, it's easier to digest then. So you see, like for earlier when we talk about beta, it's really a prior, like conjugate prior, to describe a binomial or binomial distribution, binomial trial, or something like. So in that case, like your outcome is binary. Is in that case, like for beta, it's like either uh, head or tail, or like true or false, or like or success or failure. But of course, like in many situations, realistically, uh, when you have like let's say even discrete number of outcomes, like the number of outcomes will be more than two, right? So in that case, you will encounter like multi-normal distribution, and Dirichlet is simply the extension of beta distribution, is like the conjugate prior for the multi-normal distribution. So for multi-normal distribution, let's say if I have, um, let's say, uh, n outcomes here. So let's say I have like maybe I just think of like tossing a dice here, right? I throw a dice, unless I have 6 outcomes here, like 1 to 6, right? 1 to 6 here. So I have 6 outcomes. Um, Now I can talk about the probabilities of each of these outcomes. So I can have like P1, P2, P3, and P6, right? So like beta distribution is trying to describe the distribution of the probability of head. The Dirichlet distribution is trying to describe the distribution of all these probabilities here. So you can think of this as a vector, right? So this is like some vector P here. This denote like the probabilities of like how is how like how much chance to get like getting a 1, how much chance getting a 2, and so on and so forth. And then with this P, I can just describe the distribution of this P, right? And think of like I given like this, let's say like this is like the dice having like the actual probabilities like P1 up to P6 here. So now let's say if I toss this dice like n times here, right? I toss n times, and let's say I got like x1 so many 1, x2 so many 2, x3 so many 3, and so on, like x6 so many 6 here. Then the probability to get this outcome, maybe I just call this O here simply. O given like I have like P1 up to P6, right? This would be simply what? Simply what? So it would be like P1 to the X1, right? P2 to the X2, P3 to the X3, something like that, up to P6 to the X6, right? I'm like the binomial distribution because I just mentioned that like I toss n times, I got like x1 so many 1, x2 so many 2, and so on. So I didn't specify the orders here. So of course there are multiple orders to get like the same number of x, same number of 1 and same number of 2, and so on. So therefore like I have a scaling, I have a kind of like a the number of uh, okay, I just call it. I have a scaling factor here I need to take care of. That would be simply like uh, x and factorial. Okay. Oh, I cannot write it. I don't know why. Okay, yeah. For x1 factorial, x2 factorial, and so on, x6 factorial. So, okay, don't worry too much about it. This is an extension of this NCM, NCR thing, right? You see the NCR is just n factorial and r factorial and minus r factorial. I mean, don't worry too much about that because I like this scaling factor here. If you do inference, it does not kind of like affect your result too much. So now I have this. This is the likelihood, right? This is the likelihood function. Right? This is the likelihood here. So if I want to do like kind of like Bayesian inference or even just map, I want to find, let's say, what is the my P1 up to P6 given my observation, and maybe given some prior, given some prior, maybe I just draw a vector here. This is prior here, and this will be proportional to, of course, the likelihood function here, PO given P1 here to P6 here, and then I have this P, the prior here, like P1, P6 here, and this will be like somehow parameterized by this A here. Now, as before, like, okay, this guy here is just equal to this one here, right? It's equal to this one here. Is proportional to P1 x1 up to P6 x6 here. this one, again, I can take many form, right? But I want to take the form is convenient for me to do calculation. So therefore, I want to have a form something like P1, maybe like A1, P2, A2, something like P6, A6, right? And and like the beta distribution, the actual form is I have a -1 here, just by convention. And I have some normalization factor here. This is actually, the normalization factor is simply like gamma uh, A1, gamma A2, gamma A6, and this is multiplied by gamma A1 plus, oops, let me, okay. And this, by the way, is the Dirichlet distribution. So now, without going through any of the algebra, so let me just do an inference just similar to beta we did earlier. So let's say if I start with like the parameter is like A1 up to A6 here, the initial parameter. Now I observe X1 up to X6. Now I will have an update eventually. Like this one is actually equal to, of course, it is initially a Dirichlet. So now maybe I will rewrite this. I just call this a Dirichlet here. Maybe I write this as Dirichlet here with parameter A here, or like with parameter A1 up to A6 here. And after I multiply by this likelihood, actually I will get another Dirichlet. So, and that Dirichlet again, I say of a distribution P1 up to P6 will be A1 tutor, A2 tutor, and A6 tutor. So maybe you can guess like what will be this A1, A2 tutor, like will be A3 tutor, A4 tutor, A5 tutor, A6 tutor. So it turns out they are just A1, as you can guess, plus X1. Let's see, make sure I'm actually correct. I think I'm correct. Yeah, A2 plus X2. This is like very similar to beta, right? So it's like essentially very similar to beta. But I'll skip the computation here. Like you can find uh, the, the detailed derivation in the notes if you're interested. But I'll just give the result right away. Something like that. And of course, like with this, so you can again like already do the I mean without doing this is like without doing any integral or whatever, right? You know that it starts with like a Dirichlet distribution with the parameter like that. Now you observe something basically like you do this experiment n times, and you observe like getting a one like x1 times, getting a two x2 times, and so on and so forth. Now the only thing you need to know is that you need to update your Dirichlet distribution parameters by like a1 plus x1, a2 plus x2, and so on and so forth. Yeah. And okay, maybe again I give a numerical example here. So let's say if I have like the starting the Dirichlet have parameter a1 is like 2, all of them is 2, 2, 2, 2, 2, 2 is just a dice. I have the initial parameter is 2, 2, 2, 2, 2. And now I toss the dice like 10 times, and then I get like 2, let's see, 1, 2, 3, 4, 5, 6. Let's say I get 2, 1, 1, 2, 3, 3, 3. Let's see how many I have left. I mean, I get 4, 4, and then 0, 5, 0, 6, let's say. So what will be my P, um, P1, P2, P6, given my observation, this is the observation, and my prior, that's just say, it's like 2, 2, 2, 2, 2, something like that. Of course, this will be a Dirichlet. So what will be the parameters here, like A1 tutor, A2 tutor? Or maybe I just ask you, like, what will be like A1 tutor? Mm, a I I guess maybe I'm not clear here. So this is the outcome I have, like this is the x here, x1 equal to 2. Oh yeah, x2 is equal to 1, x3 equal to 3, something like that. So we are doing something similar as before, but like now it's like extension. Of course, I skip all the derivation here, but like the difference here now we are dealing with like multinomial distribution. So now instead of like tossing a coin, I'm folding a dice. So I have like not just 2 outcomes here, I have like multiple outcomes. I can get 1 to 6 here. So I have a multinomial distribution for the likelihood function. And the conjugate pair for that multinomial distribution will be the Dirichlet distribution. And as you can see, like really, it's just having a form something like that. The Dirichlet will be just having a form like this. It's actually quite similar to a beta distribution. And you can do a derivation for that, but I skip all this because the outcome is very similar to beta. Basically, if I'm trying to do a posterior, kind of like estimate the posterior distribution, given observation and prior, of course, it will be proportional to likelihood multiplied by the Dirichlet prior. And it turns out will be a Dirichlet. And it will be a Dirichlet with the parameters will be updated as like the original A's added with the number of observations for each of the outcome. So yeah, my question is really trying to see if you guys are paying attention. So my question is like, okay, now just put in some numerical numbers for that. Now my A's will be just A1 up to A6 will be just all equal to 2. And let's say X1 is equal to 1, X2 is equal to 2, X3 equal to 3, X4 equal to 4, something like that, I think. And then X5 equal to 0, X6 equal to 0. Something like I fold the dice 10 times, and I got only 1, 1, and 2, 2, and 3, 3, and 4, 4, and then I don't get 5 and 6. Now my question is like, what will be A1 tutor here? What will be A1 tutor? Basically, it's the parameter, the updated parameter of Dirichlet, the first parameter of Dirichlet, distribution that corresponds to the posterior probability. Yes, 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 yes. Yes, yes. Uh, so it's very simple. I just want to see you guys are following. So and of course, I then you have updated A1, A2 tutor, A3 tutor, and so on. And then you can also do an estimate of P. Note that like this is the probability of, I'm showing the probability is a Dirichlet, right? But if I want to do an estimate of P, for example, I don't want to do an estimate of P2 here. So the estimate will be the expectation of P2 with a distribution with respect to this guy here, with a distribution like Dirichlet with parameter like A1 tutor, A2 tutor, and so on, like A6 tutor, and so on. And an expectation like that, actually, as you may guess, if you recall it, how beta is like, will be simply equal to A2 tutor over A1 tutor plus A2 tutor plus A4 tutor plus. So therefore, for example, in this case, if I have this initial prior, say A1 up to A6, as mentioned earlier, and maybe these are my observations here. If I ask you, like, what's the Bayesian estimate of the probability of getting a 2 will be simply equal to A2 tutor over this add together. So therefore will be equal to A2 here is equal to 4, right? A2 is equal to 4. And this is like A1 is 3, 4, 5, 6, I guess, plus 2 and 2. So that will be something like 4 over yeah, something yeah, 22, I guess, like 2 over 11, whatever. So and for completeness, like, by the way, if you want to, this is like for Bayesian estimate. If you are going to do map estimate, similar to the case of beta, you subtract all this like by, so this is Bayesian, will be like A2 tutor minus 1 here. So you have A1 tutor, A2 tutor plus A3 tutor plus A5, A6. But I guess you need to minus 6 here, something like that. You will get a map estimate. So okay, I guess of course I skip all the derivation here, but it's quite similar to beta, so therefore I don't want to spend time on this. I think you can, if you're interested, you can take it up and yeah. And the only point I kind of like mentioned this, only reason I mentioned this because this is a kind of like very common. Like I guess that you're likely to encounter like Dirichlet if you in the future, and just to make sure that you don't get scared. Okay, what's Dirichlet? I don't know. I never heard of that, but it's actually something very simple. So I have like, I forgot, is I have 10 minutes left or like 5 minutes left. Like it's like 45 or 50. I don't know. I spent quite a bit more time than I expected. Uh, let's see. We should drop me an email like mentioning about some question for, but he's not here, so I'm not sure I should talk about that. So Okay, let's see if I should maybe at least I say what I'm going to talk about next. Then maybe I will um, then go more detail into what if proof and so on in next time. So what I'm going to do next is um, we actually I guess I spent a couple classes just talk about probabilities and estimation with map and estimation and so on. Now we will kind of switch gear to go back to talk about information. So this is the title of the class. And so, but to begin with, uh, I first thing I like to mention, I guess next time in more detail would be the law of large number. Basically, if you have a random variable, it's just say if I have a random variable here, y, and if I sample it many times, like I sample it 1 time, 2 times, and so on and so forth, many times, n times. So, and if I try to compute the empirical average of that, so y1 plus y2 and so on, 1 over n, this should converge to the expectation of y. So this is known as the law of large number. So it seems like reasonable, right? And I will give at least a proof for that for the weak law of or the strong law is harder to prove, but the weak law I can prove it like 10 minutes or something like that. So using the law of large number, we can kind of give, this is a useful tools to study um, uh, kind of ID distribution. This is identical independently identically and independently distributed. So ID. And one thing is I can use this to argue that um, if I look at a random source here, let's say now I call it a random source. So what I mean by random source is let's say I have something it would kind of I can repeatedly sample this distribution, this thing here. I mean, I can repeatedly sample this thing to generate me some random variables. I say y1, y2, yn. And as I mentioned, this would be IID. Each time I sample that, they are independent and they are identically distributed. Like all of them have same distribution. Now, if I look at a sequence of that, I draw this many times. I draw some sequence of that. Then I can describe some characteristics of this sequence. Basically, I will introduce something known as something as typical sequence. So a typical sequence would be simply means that it will always occur. What I mean is if I draw this things, let's say a length n or maybe n is 1,000 or 10,000. If I draw a sequence of y with 10,000 samples here, and this sequence always possess the same characteristics and can possess these characteristics of this typical sequence. And I can kind of use some analytical basically tools here to say whenever something is yeah, okay, I guess I'll leave that later on after I give a clear definition next time. But this is a goal here. Like I want to talk about typical sequence, and then like you see like how this typical sequence should be related to entropy. That is like some of these main things. Take home message that you should learn from this class is like uh, understand what is meant by entropy, like in information theory context. Um, and actually, it turns out it's like the yeah, okay. I guess I also want to leave that. Yeah. So let's see. Yeah, that's more or less I want to do originally. Like this class is like okay, define, prove the law of large number, and then like talk about typical sequence, and and kind of like yeah, okay, yeah. So okay, maybe I should just stop here. Then this is a preview, like just for what we are going to talk about next. And of course, when we talk about entropy, then there's a number of okay, yeah, actually something to mention also. So entropy is just like one information measure of it's actually an information measure of a random variable. So if a random variable, so we want to say like what's the entropy of that random variable will be like um how random is that random variable, more or less. You can think along this direction, right? And this is like one information measure. And you can, for example, when you have like multiple random variables, then you can talk about like what's the mutual information shared between the random variable. And you can also talk about the conditional entropy, say knowing one random variable, what's the remaining freedom, remaining randomness of the other variable, and so on and so forth. Um, yeah, this is like all going to come next. And okay, I guess I really should just stop here. And uh, yeah, I guess I even like Richard is not here. Maybe just a quick comment about like uh presentation, like because I also like received like a query about like presentation. So you are supposed to present about like mid October. I guess I will try to schedule it like maybe next couple classes. Like, and and I will like you to give me also like submit an abstract and also title like to Canvas like early October as well. So that one is just um I mean I just want you to get started early, so it's not it's tough tentative. Like for example, like if you first like to talk about that, but eventually maybe like you find that it's very difficult, like you don't know how to proceed, you can definitely switch topic. But I want you to think about that early. And as I mentioned, like you can present any topic. Like so, I mean, when I say any topics, of course, related to the class, but some suggestion will be like maybe, for example, like chapters like inside Mackay's book, or like talk about some packages like um, for probabilistic programming and so on. And also like I also updated the Canvas website, yeah, with assignment for proposal, project proposal, and so on. And actually, I guess I uh, project proposal I think is still like also around mid October. So I guess a good way to manage your time will be like you try to kind of connect the your proposal with your presentation somehow. Maybe if you want to explore something uh, like on some interesting topic, you can look into that like in your presentation, and then like when you present, you will learn more, right? And then like if you find this is an interesting topic for your proposal or for your final project, then you can like propose it in your final project and so on. And for a final project, it can be I'm not really looking for original things, but uh, I would just want you to like have some hands-on experience of like things we talk about. So it can be either theoretical, like more theoretical, like because part of what we discuss will be like some information theory stuff like that. You can dig into those papers, maybe repeat some results, or even just understand the papers and try to elaborate. That's fine. Or you can just go for like some inference problem that using probabilistic approach and maybe repeat some of the experiment and then maybe try to re-implement some of this method in the literature. And of course, if the source code is already available, and then if you just rerun the source code, probably it's not fine, it's not sufficient. But it would be okay if you kind of like re-implement that somehow. Like for example, the source code is not there. They describe like how they're going to do that, and you try to re-implement that, and that's totally fine. I think it's a good project. So and that's it. Okay, like I will talk more like next time. I guess I'll see you guys next time then. Yeah, thanks.